Hey, hello and welcome to an episode of Rustacean Station. I'm your host, Alan Wyma. Today I'm with Seaton Ullberg, who is a PhD candidate. I forgot to ask what you're studying exactly, but maybe why don't you introduce yourself? Then
Yeah.
Let me butcher it. Sorry, go ahead.
That's okay. Seaton Ullberg, I'm a PhD candidate at the University of Florida, and I'm studying material science and engineering. I actually got my undergrad bachelor's degree from UF as well, so I'm kind of like a super gator, if you will. But yeah, so I'm excited to get into it today.
Yeah, we're talking a little bit about your work, right? You asked me how come I didn't send over any questions. That's because I really don't, I understand this is interesting, but I have no idea exactly what it means, right? So you wrote this, it's a library, right? I believe.
Yeah.
Yeah, you wrote this library, which measures kernel density. Well, it says kernel density estimation, which is something, right? Do you mind to kind of explain very simply, like I'm 8 years old, what exactly this is doing? Because for me, when I think about kernel, I think about the Linux kernel and OS kernels, which is probably not what this is related to, right?
Exactly. Yeah, this is very different. So I will preface saying I'm not a math major. I'm no mathematician. But generally speaking, for layman's terms, this is a statistical technique which allows you to estimate probability density function of a random variable. So if we think of, in general terms, what's a random variable, that's any one-dimensional data set, right? So we can have data points along any axis. And if we don't know a function that describes how those data points are distributed, we can use this kernel density estimation technique to calculate or estimate, rather, the probability density function of that sample distribution. And from that, we can do a couple of other neat things like sampling from the underlying distribution. So again, in the case where we don't have a way to estimate that, we can create an estimation of it and then resample points in that same distribution. So very far away from what you'd expect of like an OS kernel. The word kernel here derives from kernel functions, which are the functions that we apply to each point in the distribution to kind of get a general estimate of what the distribution is at large.
All right, there's still a lot of words in here because I never took stats in school. So I think there's a couple of words in here that I don't quite understand yet. So when you say density and probability density, that exactly mean? I mean, random variable, like when I'm thinking about random variable, it just means like some random data point that gets put into it and then what happens to it, right? You have an X, you put X inside, something comes out. Am I thinking in the right direction or no?
You're kind of on the right track. So like when we think about randomness, right? Random might not be the perfect word for most people to understand this. If you think of a truly random variable, you'd have the same number of points basically at each point, your x-axis, right? That eventually become to be a random variable. But if we think of just an arbitrary distribution and we say on a number line from 1 to 10, that the data could have a peak at, 3 or have a peak at 8. And that would still be a random variable, right? It's not going to necessarily be all centered, or it's not going to be uniformly distributed, but it could be centered at certain points on that number line. So what I mean here in terms of probability density, we think of the density as being high, where we get a lot of data points on that x-axis. So again, like I said, if we're clustered at a particular point, that's going to be a high density point, right? So if we have a peak in our probability density function, that is going to indicate that we have a lot of data points under that peak.
Okay. And when you're saying distribution, you're talking about all the points on a graph or on a data map or whatever you call it. Isn't that right?
Yes, that's right. So like I like to simplify it down just to like a 1D distribution. So like just a number line. And I think probably most people are familiar with a histogram. So if you think of a histogram where you're essentially binning all of your data into multiple boxes and then you count how many data points are in each box, that's sort of like a discrete way to do what I'm doing here with the kernel density estimation technique. Like essentially if you were to take a very fine grain bin and you put all your data points in those smaller bins, you get a smoother and smoother histogram. What this KDE or kernel density estimation technique allows you to do is to create a totally smooth and continuous probability density function, whereas a traditional histogram would be less continuous and not as smooth.
Okay. What I don't quite get is you have these random variables, but what's changing is like maybe I can be more kind of clear. Where would kernel density estimation be helpful? Or in anything, that sounds kind of rude, but I mean, where is it useful? Let's say it that way.
Yeah, so it's basically useful as a modeling technique, right? let's just put it in concrete terms. Like, let's make up an example. A lot of people are interested in, the housing market right now. It's something that's crazy. So if you were to take, for example, if you were to look at Zillow and you were to get a bunch of housing prices, that's a real number. That's a real physical number we can think about is the value of a house. And you were to plot all of those numbers on a number line, we might maybe get a part of your city that has some cheap, smaller houses going for, say, 200,000. And then there could be some other special part of the neighborhood that the average housing price is $1 million. So if we plot all of those house values on a number line, and we apply this kernel density estimation technique, and we were to view the resultant PDF of that, we would see a peak around the 200,000 value and then another peak at the $1 million value. So what that kind of allows you to do is to basically estimate an average housing price or an average price per region that you're interested in. What I haven't really gotten into yet, and what the limitation of my current implementation of this library is that it's only 1D. But if you were to think of using this in a two-dimensional sense, you could actually build what would look like a heat map over your city. So if you had a heat map plotting, X and Y coordinates, if you're looking in a bird's eye view, you could get some peaks of the kernel of the probability density function, where basically your density of houses is going to contribute to a peak in the PDF function. So that's another way to look at population density or financial data or anything like that can be modeled, but doesn't have a concrete function that you can sample from directly. So this is all for data that doesn't have like a closed form solution, you could say. It's data that you're drawing or generating that you don't have a perfect fit to. And this is a way to create a continuous function that fits it.
Okay. Actually, your Zillow thing is very useful for me to start to understand more.
Yeah.
I appreciate that, because I know I was just in US and my wife kept checking her phone and seeing what housing prices were around us as we were driving around streets of Beverly Hills and other places in California.
Yeah.
And yeah, I do remember there's quite a lot. It was like around $1 million, $1.5 million or something. Some are going up even higher than that. And of course, there were some neighborhoods which we didn't want to hang out for too long, and those were definitely lower. Maybe 100,000, 150K, etc. I mean, like, I want to go back to that example because, like I said, it's very easy for me to understand that example. To me, it sounds like I could just plot those data points, and like you said, in a histogram. Isn't that just enough for me to understand more? Or is it just that the value of this comes in when you have multiple dimensions?
No, so you're totally right. You could plot that and get some idea of the values you're looking at in a histogram. But what this kernel density estimation technique allows you to do is basically to go a step further. And the name we use for that is sampling the distribution. So what I mean when I say sampling the distribution is that you can generate new data points from a finite data set. That's a pretty powerful technique, right? So you say you have finite number, maybe 1,000 houses for sale in a large city. You have 1,000 data points that you can work with, but you could also generate or resample that distribution infinitely many times, and you would get all the possible prices with realistic or measured probabilities, right? So if you were to look at it in a histogram, you can certainly do that. But if you want to do some sort of an iterative technique or a solver or something that requires resampling of your underlying data set, then that's where you're going to need this kernel density estimation technique to get a continuous distribution and a distribution which you can resample.
Do you mind to start to apply something with kernel density estimation so I can understand how this would be better? Because I'm still having a problem trying to understand in my head. I mean, because I can understand looking at your graphs and thinking about the peaks and saying, okay, there's a lot of houses that are here. There's a lot of houses that are in this price range. Obviously, if you say 100,000 to 150,000, because they talk about things in 10,000 instead of talking about things in 100,000. So that's why I'm thinking. So we have like 100,000 to 150,000 over here, a bunch over here. You got $1.5 million, a bunch over here, not much in between because of, like you said, the peaks. And we could be talking about different areas, right? Obviously, certain areas are better, especially if you look at another dimension could be, okay, that school is really good, therefore the housing price goes up. Or maybe the school is so good because the housing price is so high they can afford better teachers, etc. I'm just trying to think about how would I want to use this to say maybe choose the right house for me based on different kind of factors.
Yeah, so it's interesting that you've introduced new factors, right? You're talking about the school system and the relation to the housing price. So let's kind of step back and look at multiple dimensions. The way that I have seen kernel density estimation be used in particular is for model development. So we're talking about the distribution of each of our parameters. That's something that we're interested in understanding in a continuous sense. So if we look at, for example, in most models, right, your housing price would probably be the output variable. Does that make sense?
Yes, in the end,
So
yeah.
that's like yeah.
I mean, think about a normal person, right? You would care about that, right? How much do I have to pay for this, and what am I getting out of it, right?
So let's take a few more factors. Let's consider the house's distance from your place of work, maybe the grade of the nearest school, maybe the number of bedrooms, maybe the square footage. Those are all numerical factors that we can put into our model, right? So those are all things that we could create a distribution from. So say we have 1,000 houses, we know the target value, which is the price, and we know the factors, their parameters that we're considering in our model, like I said, square footage, distance to work, things like that. So each of those parameters that we're using to predict our output target property is going to be one dimension or one variable that we can model with kernel density estimation. So if we look at using KDE as a technique to understand that underlying distribution, let's say we apply this kernel density technique and we find a peak of data points that have a close distance to work and a large number of bedrooms or something like that, which is what you're interested in, maybe if you have a large family. And you can understand how that region of your parameter space corresponds to a certain number in your target space, which is your housing price. So again, if we were to apply some sort of like I'm going to add some more terms that are probably not well known, but maybe if you had an evolutionary algorithm or some other type of a iterative solver, you would want to resample those parameter spaces more densely or more robustly, right? And since we started our example by saying we only had 1,000 data points, we're going to need a lot more data points to train an efficient model. And we can generate those data points within a reasonable amount of probability using this technique, right? So if we say that there's a region of space where it seems like we get a lot of points with these particular parameters, we can sample that really densely with the generated PDF, and we can build a better model because we have more data points that are physically informed because of the original underlying 1,000 data points that we got. I'm not sure if I led you astray by introducing some more concepts there, but I hope that it will.
A little bit, no, but I'm just thinking,
Okay.
obviously, when you do have more dimensions, you definitely need more sampling, right? So sampling obviously just means more actual data to plug into your algorithm, right?
Yeah, exactly. So this is what I'm trying to get at, right? Is that you can basically generate more data by using this technique. And it's not like you're generating data in an uninformed sense and in a statistically non-valid sense. This is data that fits the actual probability of the data that you already have. So we're just creating data points that are similar to your existing data points, but slightly different. And you can evaluate those in your model and see either to train it or to evaluate its performance on a slightly different distribution than what your underlying one is.
Now that's interesting, right? But I think something to keep in mind too is what about noise? Or what I call noise. I'm not sure if that's a proper term where it's like,
Mm-hmm.
okay, this is a house that theoretically, according to the model, should be X, but maybe it's like X divided by two because like maybe in that house there's been a murder or something. I'm just trying to think of
Yeah.
something that would
Right,
drop
right,
the
right.
property value, or it's next to, or even sorry, maybe I don't need to be so grim.
No, that's okay.
Next to construction, right? Because nobody wants to
Yeah.
be next to construction of like say like a giant building that could,
Mhm.
overcrowd. It could block out the sun. It could, whatever. Like, have you seen the movie Up?
Yes.
So remember his house is kind of like in between a bunch of really
Yeah,
tall buildings.
he's the last
Yeah.
one to leave.
So his house, I mean, is I don't know. It could be worth basically nothing unless the land is actually worth more, right?
Mm-hmm.
So this kind of stuff could be very interesting to see. How would something like KDE, kernel density estimation, handle some noise like this? I mean, is there something you have to do in order to kind of stop this problem?
Yeah, that's actually a great point. And that kind of brings in another piece of the puzzle, the KDE technique, right? And a part of it that is actually super critical to getting accurate estimates that I haven't brought up yet is a term known as bandwidth. And what bandwidth essentially corresponds to, maybe in layman's terms, is basically the smearing width of the kernel function that you're applying to each data point. So if you go back to our original example, thinking about like the Gaussian or the normal distribution, we can scale that distribution to be wider or narrower, and amount of width corresponds to what we call the bandwidth in KDE terms. So if you want a model that is very accurate or very narrow in its generalizations to your underlying data set, you would use a very small bandwidth value because that would create small, sharp peaks over each data point. But if you were okay with kind of exploring the space a little bit more and getting a broader generalization, you could use a wider bandwidth, and that would create a wider kernel function over each data point, which would be a broader overall PDF. So that is kind of one method that we can use to tune the accuracy of the generated probability density functions. And there's a whole slew of ways to determine what the optimal bandwidth is that I won't get into, but that kind of does get into your point of understanding how we can work with outliers, and do we want to be sensitive to those outliers, or do we really want to kind of cut them out of our underlying data set?
Okay. Yeah, but like you said, if you have a wider bandwidth, then that would kind of make it less accurate per se, right?
Generally speaking, yes.
Yeah. So
Yeah.
you have to kind of weigh your options.
Right.
Okay.
Right. And like I said, there's optimization techniques to find, a bandwidth that is too narrow and not too wide, but that is some pretty advanced math.
Okay. Yeah. I mean, does KDE work with, is there like a set limit of how many different dimensions you'd want to add in, or is it just kind of up to you? And then the more data points you add in and the more dimensions, and then maybe longer it should take to calculate?
Yeah. In terms of the computational efficiency, definitely it gets hard when you get into more and more dimensions that you're working with. But really, from a mathematical standpoint, there's no limit. You could have, 1,000 dimensions and it would be still the same technique that you're working with. But in terms of the actual, the implementation of it, it would be very hard to calculate that. But you do have to think about, if you're calculating these distances and high dimensional spaces, we kind of run into this problem, which people call the curse of dimensionality. And when you're working with high dimensional models, it can be hard to understand what distance means because you have so many dimensions over which you're calculating. That distance becomes a less important metric in higher and higher dimensional spaces.
Okay. Now, KDE, I mean, there's other competing ways to do the same thing, right? So how much weight should I put into it? I mean, I think that people say like you can look at facts and then you can derive whatever conclusions you want from it. Like we can go back to the up example and say, okay, but this house is, worth nothing because it's in the middle of these things, but you may not even look at that and just say, okay, but I'm just trying to think about like how much weight should I give to KDE versus like other competing algorithms?
Well, it's kind of interesting you mentioned that. I feel like KDE is so broadly applicable to things and it doesn't get as much use as I would like to see. It seems like so many people jump straight into, AI and these really deep neural networks before they try and apply these simpler statistical techniques and use more of the older numerical methods, which I think KDE would fall into. But in terms of like competing algorithms, it's hard to say that there is one that is exactly like what KDE does, because the real value I think that KDE gives, that it has this property, which is that it's non-parametric, right? So you don't need to apply any weights to your data points to get a density function out of them, right? You can alter the weight of each data point, but it's non-parametric in the sense that you can just plug in a data set and you can get out a smooth, continuous density function from which you can sample. So it requires basically no prior knowledge of the data that you have, and it can create a estimated description of all of the data points in between, which I think is a really powerful tool. And I'm not sure if there really is a competing algorithm that does just that. When we get into the higher level stuff, like how it can be used to model things or how it can be used in parameter selection, sure, there's a lot of competition there. But from a lower level standpoint, it really is kind of a class of its own.
And when you say non-parametric, I mean, to me, that means obviously not about no EMTs. It's talking about parameters, right? I mean, inputting data.
Parametric. Yeah, parametric.
Parametric, sorry. Yeah, see, my English is getting worse. I live in Hong Kong for too long.
Oh, wow.
So non-parametric, that's talking about parameters? Is that what I understand correctly?
Yeah. So you don't need to parameterize the KDE for it to do its thing, essentially.
Now, what does that mean exactly if I want to parameterize something or not?
So, like, if we think about what it means to require parameters, right? It means that you need some metadata or some sort of, what's the word that people use all the time? Hyperparameters. People talk about hyperparameters a lot in relation to like machine learning and neural networks like that. And you don't have the only parameter that technically could be assigned to a kernel density estimation would be that bandwidth that I mentioned. But again, those could be sampled from the data itself. You can determine the bandwidth from the underlying data. Whereas a parameter, like, for example, in a neural network, you have a parameter like the learning rate or maybe a dropout rate if you have that built into your network. And those can drastically change the performance of the model. So it's nice to have in KDE no need to worry about optimizing those parameters that are required just to get a result out.
Okay. For me, I'm a little bit familiar with AI, but not so much. What I understand is that you can train it the same with this KDE, right? So you're giving it some samples. It's kind of coming up with some type of algorithm to plot, right? So if I want to reuse that algorithm, I mean, I can only use it. This every time I want to draw that up, I just keep adding more samples to it, and then I could just use that graph to figure out where something will be based on the KDE. Is that right?
Oh yeah, if we're talking about in KDE terms, that PDF, that probability density function, is basically what's going to describe where you're most likely to find your data points. So yes, you're accurate in that sense.
Okay, so then I would just say, okay, I got my KDE over here, and then let's say I have multi-dimension. Then I would kind of start to plot, okay, with these dimensions, based on what I know about this thing, about this sample, right? That's not part of the KDE. I could then go to the KDE and say, okay, here's the thing that should be in this area, right? Like basically like coordinates.
Yeah, basically. Yeah.
Okay. That's interesting. If I find enough samples that maybe don't fit the KDE, then obviously I should say, okay, maybe my KDE needs to be adjusted. Let me add that to my samples I used to generate this one and then regenerate. And that would kind of help.
Yeah. So if you're talking about bringing in new data so if you have maybe if you split your data set, right, and you wanted to do like a train test type of thing, and you built your KDE on one set of data, and then you find that it doesn't generalize well to your other set of data, clearly the best thing you can do to get a better fit would be to just include all of the data, but then you kind of beat the purpose of the prediction, right? But yeah, so if you needed to improve the performance of the KDE just with the subset of the data that you wanted to, the thing you can do there, you can either change the kernel function. So again, I said that most commonly people use a Gaussian or a normal distribution as the kernel function, but you can also use what's called an Epineshnikov kernel function, which kind of looks like an inverted parabola, or uniform distribution function, which is just like a step function. And that'll change the shape of your PDF. So it'll be maybe less sensitive in the regions that are data heavy, or you'll get a quicker drop off in the PDF in regions that are very sparse in data. And that'll change your final estimates when you're resampling that data. So the choice of kernel function is a big factor to change your KDE performance. And then also, we talked about before, the bandwidth is one thing you can do to get a very different resulting PDF.
So now I have a really good question, right? If I generate my KDE, right, I got my graph out there, and it just looks like noise, just basically like very badly constructed stairs that nobody wants to climb, right?
Mm-hmm. Okay.
I mean, I could say, okay, how would I know if I need to fix my bandwidth or if I need to change my kernel function?
Okay, that's an interesting question. I would say if you're finding that, it's sort of hard to address, right? Because if you find that the PDF doesn't align with your expectations, that could be a problem of your data set, right? So because, again, KDE is a technique that is just interpreting the underlying data, the first place to turn is your data set, right? But if you are confident in your data and you think it's clean and you think it doesn't have crazy outliers or anything like that, then what you can do basically is, I would say, the bandwidth is going to be the most critical factor. So if you have a very narrow bandwidth, you'll get a much closer estimation to the underlying data set, and a very large bandwidth would be more general. So it depends on your use case. If you want to be very close to the underlying data set and you don't want to explore that feature space much, I would say really cut down the bandwidth. Otherwise, if you're interested in exploring and that PDF is kind of showing a broad peak over your data points, then maybe you can play with the kernel itself. So it really does depend on your use case ultimately.
But is it also possible that what if I have these dimensions? Right, let's go back to housing, because that's just something that goes to everybody. Everybody needs to stay somewhere. Nobody can stay in a cardboard box for too long.
Yeah.
Right. You got these different dimensions like school, how close it is to you, etc. Right. I think that how close it is to where you work is a good example. And then let's just look at straight cost of the house.
Okay.
Right. Obviously, the cost of a house doesn't matter where you work unless you work in a very big place like Google or Amazon, these kind of FAANG companies. It doesn't really matter in the cost, right? If you work in some small office space somewhere. But you have these kind of dimensions and then you throw data at it and it just, you're going to have noise no matter whether you change the kernel function or you add more sampling or you increase or decrease your bandwidth. I mean, basically, you're kind of wasting time to even plot these kind of, like you said, the best example I have in my head is you work in a place that is not big enough to cause an effect on the housing market. So if you looked at dimensions like that, then no matter what you did, this would basically wouldn't do anything to look at the cost of the house. You have to actually look at things besides cost of house, it's also what's the value to me, right? How much time do I save? These kind of things like that, right?
Mm-hmm, mm-hmm. Okay, so let's just see if I can maybe rephrase that in a way that helps me understand better. So you're saying that maybe the data that you have available to you doesn't seem to have any solid collinearity with your target value. Maybe it doesn't align well, is what you're saying?
I guess it could be like if you take these different dimensions that are very personal to you, but then you plot them to try to figure out the price of the house, wouldn't that be a little bit confusing? Or maybe I'm thinking way off topic over here. I'm just thinking about adding dimensions of things that are so not dependent on that you could be really lost.
Absolutely.
Right?
Yeah. So, I mean, I feel like I was kind of just spitballing possible parameters for what could influence the price of a house. But, like, say you work for Zillow and you want to come up with an estimate of a housing price. The first thing you need to do is to understand, okay, what influences the price of a house. So if you just throw random data like, oh, the amount of mailboxes per square mile, like that's not a great dimension to throw into your model. That's going to, like you said, increase the noise, and that's going to make a poor estimate for the overall target value. So that is a question that I would say that's something you should address before you even apply techniques like KDE, right? Because KDE won't necessarily be able to tell you like what is a good or a bad dimension. You might notice if you apply a KDE technique to a dimension that doesn't have a significant correspondence with your target value, you might notice that you get kind of just a broad or flat peak across over all of the data. You won't see any clustering of this value seems to have a strong correlation with the target value. And maybe you can use it as an exploratory technique in that regard. But generally, yeah, it's a problem of modeling in all fields that you have to understand. You have to have some information as to what are the factors that create a stimuli that will influence your target variable. And that's something you have to address before you get into the statistics of it.
Well, I mean, is there a way that I could say, look at things? I mean, because obviously distance from your work to your home is something easy to measure, right? To me, if you're not really paying attention, that just sounds like a pretty valid point, right? But then you're actually measuring value to you, but not value to market,
yeah.
Right? So, but if you're not paying attention, like, is there a way that you could say, oh, is there a way that KDE can kind of say, this dimension that you added is actually not fit for this kind of model? I mean, I'm guessing probably not. That, like you said, maybe it's more of an issue of just
Yeah.
yourself, and you have to kind of think more. Okay, does this actually make sense?
Yeah, no, so that is not what KDE is designed for. There are definitely statistical techniques out there to do that. One is called PCA, Principal Component Analysis. I don't want to give a lecture on statistics, but that does exactly what you're asking for. It ranks the dimensions that you have in your data set by their sensitivity to the target value. So that is definitely something that is a super useful exploratory or data exploration technique, but it doesn't really have any crossover with KDE and what I've written in my library. So they could be used in conjunction, but yeah, PCA is just the better technique for that kind of a job.
Yeah, I noticed you smile, but I'm just thinking, I've done crazy stuff before where I've thought about something and then went back to it and like, that doesn't make any sense.
Yeah,
Well,
yeah.
I'm even thinking about that.
No, that's definitely a common problem in modeling, and there are techniques out there for it. That's just not what KDE is for.
Yeah, I'm just trying to think of something that makes sense. I mean, you could do the typical like, okay, I don't know, when I scratch my right arm, my left arm feels a little bit tingly, but does that mean that everybody has this problem? I don't know.
Hmm.
According to me, yeah, it does. But
Yeah, if you want to generalize out, of course, that's right.
or whatever. I'm just trying to think of something that actually happened to me, but
Yeah.
nothing's coming to mind.
I think if I give a better example of like, I think a way that people can use KDE concretely, it's if we think about situations where you want to, in my experience, right, I did some undergraduate research fitting potentials for interatomic interactions. So that's going to be a whole thing that not everybody's understand, right? But basically, a function that describes the interaction energy between two atoms. And it turns out that that is a function of distance. And if you have some parameters, call them A, B, C, that influence the shape of that function, that is something that really is amenable to these evolutionary or genetic techniques, basically, where you have this multi-dimensional parameter space for, of course, your A, B, and C parameters. And we can talk about that in the same sense that we talk about housing prices. And if we want to evaluate the effectiveness of those parameters, we have a finite number of data points, right? We have a finite number of, say, these interatomic interactions. They have a particular description, and we might have a experimental value that we want to get close to, right? So our experimental value is our target value, and we're generating all these with some sort of simulation engine. But if we want to create an optimal value for these A, B, and C parameters, we're going to have to really densely sample those three dimensions of parameter space. And in the cases where we can find that particular combinations of A, B, and C poor results, we can kind of cull out those parameterizations and sample more densely only in the regions of space where A, B, and C do yield a combination that is really close in line with the experimental value. So that kind of combines KDE with what's known as Pareto optimization. Basically, you take the Pareto front of a set of data and then you iterate through that process to apply a more dense sampling to the regions that were effective in producing good results. So I know that I threw a bunch of new concepts out there, but that's kind of what got me to write up this library in the first place. So I sort of wanted to share that as my real inspiration for it.
Yeah, I mean, I kind of want to get more into like why did you bother to write something like this? Because I mean, it's an effort, right? As you can see,
It
there's a
is.
lot of stuff involved, a lot of math. I mean, you're not really a math guy, so are you sure you really want to get into writing something like this?
Yeah. I mean, it is a lot of math, but it's math that has implementations in other languages. Like there's a SciPy implementation in Python, and it's something that I am comfortable writing because I can look at other people's implementations, and then of course I can also verify my results against those well-established results. So like if this was something that was totally obscure and didn't have an implementation in another language, I would say no, I'm not comfortable doing this. I'm not comfortable publishing this. But because I have verified it and I have been able to read other code in other languages, yeah, it's not so far out of my realm, of course, because I've used this technique, as I mentioned in my research a few years ago. I understand how it works generally and I understand how to apply it. So I'm comfortable writing it in Rust. And I thought it would be nice to have an implementation in Rust because I guess one day I hope to be able to use Rust more then I use Python. So this is kind of like a small step for anybody who does similar work to me. They might be able to get some use out of this and use Rust, which is, I think, a pleasure.
Yeah, that was kind of a follow-up question I wanted to ask is, like you said, that this kind of thing is definitely has something written in Python because Python is just kind of more general computer science, or not computer science, statistic, etc. languages out there. Why bother to rewrite it? Because I'm sure that's already backed by a C library that is very well tested. So, I mean, is it just because you love Rust so much that you thought this would be something to do, or were you just bored on a Saturday night, or what was kind of the thought behind it?
Yes, those things factor in. I do like to use it as a practice. I like to use it just because I think it's a fun thing to do. But I really do see that the kind of the higher level features in Rust, like I mentioned, I use traits a lot to implement both the bandwidth selection strategies and the kernel functions. And if you were to tie into just the underlying C library that is used for the Python implementations, you wouldn't exactly have the flexibility, right? You'd be kind of concretely locked into those functions that they have available in C. So sure, this one will never be as fast as the super optimized C version, but I do think that it is just a nice thing to have if you want to do statistics purely in Rust, if you want to have a data analysis pipeline purely in Rust and be able to work with all the nice things that, Cargo offers in doing that. It may not be the fastest implementation, but it is very user-friendly implementation, if I may say so. I think it is. And so that's basically kind of why I did it. I did want to do it as something to show that I could, and I also think it's something that the community could benefit from.
I think there's actually a data science group or something within Rust. Have you seen it yet?
Could you expand on that?
I forgot the name, but there's a guy named Luca Palmieri. Sorry, it's machine learning, maybe.
There's a LinFA library.
I'm not
Is that what you're
too
looking at?
sure exactly, but I know there's a group, and I remember Luca used to run it, but I'm not too sure if he's still doing it. So I was kind of curious if you're planning to kind of push this into that community, let them know about this library. Maybe you'll get some better feedback than just kind of putting it out there and seeing what to say.
No, I would totally be interested in getting it into the hands of whoever would be able to maintain it the best. It's still in the early stages, and I want to implement the multivariate distributions. Like I said, it's currently limited to univariate, but I'd like to try my hand at implementing it in a multivariate way. And then I feel like that's a full implementation, and that would have a place in some sort of a statistics library or a general machine learning library alongside. I think in LinFA, that library, it does have a PCA implementation, like we just talked about. It has some clustering techniques. It has stuff that definitely would work well with kernel density estimation implementation, but I didn't see that they had one already written. So yeah, ultimately it would be nice to get it maybe pulled into a repository like that and have better maintenance on it.
Yeah. You talking about Algo Luca? Is that what you're saying? You said the word about Algo or something? Sorry, I just wanted to share with you before I forget, and maybe other
Oh,
people can take a look at it. So, Algo Luca is the name of the Twitter account for Luca Palmieri.
okay. I'm not familiar.
Yeah, I remember he was in the space. I'm not too sure if he's still in that space or not. But yeah, I mean, there could be something there. Like I said, I think it'd be good to hear some feedback of people who are already in Rust, who are in machine learning, that can kind of give you better feedback and maybe help push us, or maybe bring it into whatever they have going on. Because I know that
Yeah,
people in
exactly.
Rust they want to replace Python. Everybody
Yeah,
wants to replace Python.
yeah, of course. I looked it up right now. There's a GitHub organization called Rust ML, and that has the LinFA library that I was talking about. And I think that would be maybe a home for something like this.
Yeah.
It would fit in really well there.
Yeah. So I think, is this the right group? Yeah, this looks to be the right group. So Luke Math Walker, his name, he's got an orange background on his avatar if you look at the
Oh yeah,
people in
I
the
see him.
group. Yeah. So yeah, maybe this would be something for you to take a look at. Like I said, maybe handing it over, because there's probably a lot of work to do. Plus, it'd be nice to have help, right?
Yeah, it's always nice to have help.
Yeah. Cool. I mean, yeah, this is interesting, and I appreciate you taking the time to explain to me about this. I wish I took stats in school, but
Yeah.
no
Yeah.
time.
No,
And
I
it's
understand. It's
too
not
much math for
exactly,
me.
it's not the sexiest subject. So it's understandable.
Cool. But yeah, to go over your library, right? The name is Kernel Dash
Yeah, it's just kernel density estimation.
Kernel Density Estimation. Yeah.
I was not super creative.
Yeah. No need to be super creative. And it's already up on Cargo, right? So we can just
It's
find it
already
there.
up. Yeah, you can look it up on GitHub too. But yeah, if you look at like the docs page, it's already built, and it is on the crates.io page as well.
Now, I do have one quick question, right? Is that I found it interesting that you have Float 64 as a feature that you can configure or not. Is it because there may be some 32-bit machines out there that can't handle Float 64, or?
It wasn't necessarily for that. I've seen in some other scientific work in Rust, there's a lot of people use the num traits library, right? Where you can kind of have a generic float that is either concretely implemented as a 32 or a 64. But I just chose to do that feature because I think it's easier to work with concrete implementation from the start. Say you have a project or a pipeline and you're using 32-bit floats, you can just not use that feature and it'll reduce the precision of the results you get from my library. Or if you do want to spend the extra computational resources to use that F64 and get the higher precision, that's up to you. So I'm supporting both 32 and 64. I think most people would do it with the num traits library, but that may be a thing that I do in the future. I just thought it was easier to have it as a feature rather than having the trait in the signature and then converting that to whatever I use internally. This way, it's just constantly the same float type throughout all the manipulations that I do in my library.
Yeah, this is pretty cool, and I feel smarter after talking with you. I feel like, okay,
Great,
I know
great.
what's going on.
I'm happy to share. Yeah.
If anything came out of this one, at least I understand what is kernel density estimation, how it could be useful.
Awesome. Good.
Hopefully, I'll be a homeowner someday. Sometimes it's nice to pull out a bunch of charts and act like you know everything, and then say, no, the housing price is too much. Look at my kernel density estimation that I put this function in with this Cartesian chart and this sample data. This is not correct. You're trying to cheat me.
Yeah, tell the realtor that and see what they say. That'd be great.
Yeah, that would be fun. I'm sure I'm going to forget by that time, but it would be fun to see it.
It would be, yeah.
Cool. Again, thank you for your time, and I appreciate you taking time to explain this, and I hope that, maybe this could be something that people in data science community can use. I mean, obviously, right?
Yeah, cool. I mean, just want to say thanks so much for having me on. It was kind of a shock. I didn't think it would get that much attention from the Reddit post, but it's cool to get some more, notoriety in the community for it. So that's awesome. Thank you.
Well, if you post late at night, it's most likely I'm going to see it because I'm on the other side of the world.
Okay,
so
yeah.
If you post it at the middle of the day in US, then I probably won't see it.
Okay.
Cool. All right. Thank you so much.
Good. Thanks.